Hello, everyone, and welcome to today's webinar entitled Industrial 3D Printing, 10 Basics in 20 Minutes. It's going to be a fast-paced and very interesting webinar, and we have two experts in the field, Fabian Allefeld and Patrick Schrader. Patrick is Head of Applications Engineering and of the Additive Minds Academy at EOS, and Fabian is Senior Manager of the Academy and Consulting at EOS North America. Patrick and Fabian, welcome to the webinar.
Thank you very much. Looking forward.
Let's dive right into the questions here. And Fabian, let's lead with you. What is 3D printing, additive manufacturing? Are those things the same thing?
That's a really good question. And to answer your question, complicated, they are the same and they are not the same. So 3D printing typically is referred to as a term by the general media and is a very broadly known term that also includes additive manufacturing. But typically, if we refer to additive manufacturing, we do talk about more robust and final part production processes. Whereas with 3D printing, we oftentimes refer more to desktop type systems and prototyping. So that means if we really talk to the industry and if we talk about serial production, additive manufacturing is the broadly used term.
Awesome. Patrick, a question for you. The types of 3D printers and materials, I mean, we know there are multiple types of machines out there, and I think there's some confusion out there about the different options. So what are they?
Yeah, let me thought that for you. So additive manufacturing is not a new technology. It has been around for about 30 to 40 years. And over the last 40 years, various forms of additive manufacturing have emerged. And today we basically distinguish 7 additive manufacturing technologies. And I will focus on the differences regarding the source material, so powder, filaments on coils and liquids, or the focus engineering source, like laser, infrared, air, or UV. Other differences between these technologies are, of course, build volume, part size, build speed, achievable resolution, and accuracy. So what are these 7 technologies? So first we have the stereolithography. That's the first technology. That appeared in the early 80s. And the source material here is liquid photopolymer resin. And this is usually cured with a laser. The second method and the technology is material extrusion, better known as FDM, fused deposition modeling. Here we work with filaments, with melted plastic extrusion, and this is fused with air. The third technology is material jetting. Here we have liquid plastics and metals, and these are cured with UV or with heat. The next technology is binder jetting, and binder jetting is based on metal powder or even sand. And here we work with joint agents, with bonding agents, and this is cured with heat. Powder bed fusion is a very popular technology, and this is actually where EOS comes from. And here we work with powders, metal and polymer powders, and the energy is provided with a laser, with a CO2 laser. And the next technology is direct energy deposition, very new technology in the late 19th. Here we have metal as the core material, and this is fused with the laser. And finally, even this 7th technology is called additive manufacturing. This is sheet lamination. And sheet lamination is a paper, basic, composite, and this is fused with heat. So this is what we have today in the market, 7 technologies. And when you want to choose the right technology for your purpose, you should ask yourself some questions like what resolution, what tolerance, what surface, what part properties, quantity, etc. I want to achieve. And then you surely will pick the right technology. And regarding materials, we have basically 3 different groups of material: polymers, ceramics, and metals. And when it comes to metals, what can be processed might be the question. And well, basically you can say what you can sinter. So you can sinter those metals that can also be welded. That is just a ground theory. What you can sinter is also been welded. And when it comes to polymer, in principle, most thermoplastics and photopolymers are sweet for additive manufacturing. So just name some materials that usually been used in additive manufacturing. On the metal side, we have the good known aluminum, tool steels, titanium, copper, nickel alloys, maraging steel, stainless steel, so actually a wide range of materials. And on the polymer side, the most used material is PA12 and PA11. And this is a polyamide nylon material. But of course, there's far more to on the market available. We have thermoplastic elastomers, we have polystyrene, we have ABS, PET, so actually a wide range of materials in the field of polymer. But let me finally give you a hint about what is the material trend, what comes in the future. And of course, sustainability is a core when it comes to material development and material usage. And I would like to point out one very interesting material. It's called PLA. PLA is polylactic acid. And this is a polyester produced by fermentation from a carbohydrate source such as starch from corn and sugarcane. So this is the future in polymer, biocompatible materials.
Fabian, Patrick told us about multiple technologies, multiple different machines, multiple different materials you can run on those machines, but why do this? What are the benefits of using this technology?
Yeah, that's a good question. It can be very overwhelming if you are first starting out with additive manufacturing. You hear all about all these different technologies and all these materials and different terms, and some people talk about melting and some people talk about sintering. By the way, most technologies that have sintering in the term are also melting technologies, such as DMLS. The S is now standing for schmelzen and not sintering. So the technology really has advanced a lot in the past. And we are at a point where the industrial adoption is widespread throughout most industries. And why are industries such as the aerospace and the medical industry adopting additive manufacturing so significantly is that because there is such amazing core benefits to additive manufacturing that no other technology can really provide. And typically, I like to structure these benefits into two sections. The section number one is high performance, complex, and even sustainable design. And the other section is also high performance and sustainable value and supply chains. So let's talk about the design part. So typically what you hear about a lot in the additive manufacturing industry is that complexity is free. And that means that you can design parts with performance in mind, meaning that you can lightweight parts. You can take out material due to the layer by layer process, and therefore really only use material where you actually need some material to go through and cover certain stresses, right? We can integrate parts and functions all into one print, meaning that we can take out assembly steps in the final manufacturing processes. One example is that you can print a hinge all in one piece. But what's actually also quite unique is that not only can you create complex designs, you can also create custom designs. And here, if we talk about the future of consumer behavior, where every consumer is interested in having something unique, also this complexity is free. And we can 3D print custom orthotic insoles, for example, for each individual patient without the additional cost of tooling, which we have in the conventional manufacturing technology. And if we talk about the benefits of supply chains and value chains, also here, the flexibility of additive manufacturing really creates a unique benefit to the current manufacturing industry and also to the current challenges that we are receiving right now in the world with our supply chain shortages. So we can move away from large centralized manufacturing facilities where we ship these products all around the world, and these manufacturing facilities can be a bottleneck and create a domino effect throughout the supply chain. And we can move towards more localized, small manufacturing cells that produce parts on demand for the customer with then also customized features. And therefore, we can really relieve the supply chain of all the complexity that we've implemented over the past decades. And yeah, what's also quite interesting is that with additive manufacturing, one example with the DMLS technology, so direct metal laser solidification, we can implement circularity. So all the material, all the powder that I don't use, I can push back into my value chain and reprint. So there's virtually very little waste in the additive manufacturing process, which also then supports the impact onto waste and onto climate change. And if we take it even one step further, and if we connect the design and this value chain innovation through a digital value chain, and being able to connect consumer behavior with production, then we really enter the true stage of Industry 4.0 environments, where one great example is Fitz Frames, an eyewear company, where I can scan my face with an app. This app creates a digital product, and this digital product is then printed on demand in a local production facility and then shipped to my home. So I have a fully localized but also digitized value chain where I can create virtual and physical products on one click of a button.
Fabian, you mentioned challenges in the value chain. There are challenges in part making in every form. And tell me about the main challenges and limitations of what you can print. What can you print?
Yeah, I mean, every technology has its challenges, and so does additive manufacturing. And to me, there are technical, there are economic, and there's also human challenges that the technology is facing. The biggest technical challenge in the end are that you need to understand the process in depth in order to push the limits of additive manufacturing. And if you think about it, that also applies to all other manufacturing technologies as well. And here we just need to also be aware that additive manufacturing is a technology that requires engineers and production teams to understand the technology. So if we talk about metal, sometimes lower overhangs can be a bit of a challenge that needs in-depth knowledge on how to adjust processes. But also with additive manufacturing on the metal side, if you're out there and you have some experience already, also with DMLS, you can print support-free and with overhangs close to 0 degrees, but you need more experience in order to do that. Sometimes long and angled channels can be a problem because you need to get the powder out. As Patrick mentioned, most of the industrialized processes are powder-based processes. So you really need to think about post-processing as well once you enter into the design phase. Post-processing can be a limit because some organizations really don't necessarily understand that additive manufacturing also has some post-processing steps in place. So we really need to design and imagine parts for the whole process chain versus just for the additive manufacturing process. But if you think about the benefits that I just mentioned earlier, really that means that you need to take a look at the whole value chain of additive manufacturing. And also here, that is the same fact in all other manufacturing processes. One other challenge that you need to be aware of is, of course, the economics. Additive manufacturing adds tremendous value to high complex geometries, to mid-range volumes, to complex value chains. But very simple parts like a fork that are high volume, where we have highly established value chains with conventional manufacturing. Here, additive manufacturing not often or not necessarily can be a cheaper solution than conventional manufacturing. So you really need to look and rethink your whole product in order to reap the benefits of additive manufacturing and add these additional functionalities such as lightweighting or functional integration or customization in order to really become cheaper than conventional manufacturing and also have the supply chain benefits as well. But I think the biggest challenge, because all of these other challenges have been solved, and there's hundreds and thousands of companies out there that produce additive manufacturing for zero or use additive manufacturing for zero parts. The biggest challenge is the human challenge, and that is why we're here today, is that more and more engineers need to understand the benefits and the limitations of additive manufacturing. We need to understand how additive manufacturing can add value to our products, to our portfolios, and to our business model in order to help us to use additive manufacturing to increase our competitive advantage in a highly competitive market. And once we have solved this human challenge, all the other challenges are basically zero because we can use them to our advantage.
Patrick, over to you. Question, both yourself and Fabian, you've both made a compelling argument for why we should use 3D printing. But who is using 3D printing? What industries will use this technology?
Any industry, but only if you have done your homework right, identifying a real problem worth solving with additive manufacturing. Because I have seen thousands of applications in my life, and I would like to share my best 4 learnings out of this time. So first of all, start always by asking yourself what problem you want to solve. Then work backwards to the solution and then towards the technology. My second learning, the best AM use cases were usually invented from scratch. Third, redesigning a conventionally manufactured part into an additive part is the second best option usually. And finally, typical 3D printing applications can't be produced in a conventional way. But let's take 3 industries as an example. Let's take the aerospace industry first. The aerospace industry is known as a very regulated industry. And this is due to the fact that they have to meet high safety standards for any component in an aircraft. And at the same time, this industry offers incredible high potential for additive manufacturing. Aircrafts consists of up to 3 million components. It is therefore of great interest for this industry to reduce the number of components and the weight through smart designs, and therefore the carbon footprint. The automotive industry. The automotive industry compared to other industries is by far the most cost-driven industry. And this strong competition is forcing manufacturers to offer even lower pricing. Today, I just took this number. There are approximately 110 automobile manufacturers worldwide. The number of registered vehicles worldwide is estimated at around 1.3 billion. So additive manufacturing can play a crucial role and play to its strengths, particularly in lightweight construction, mass customization, spare part business, and customization. And finally, the medical industry. In this case, additive manufacturing plays a special role in this industry due to its unlimited customizing possibilities. Remember, in the past, for example, orthoses were available in sizes S, M, L, XL. But that does not fit the reality. Today, it is possible to manufacture orthoses individually for each person on this planet without an additional effort. We call this process the scan-to-print process.
Patrick, a follow-up. You talked a little bit about application in the medical realm. What about applications in other industries? You mentioned a bunch of industries here. What kind of parts can you make?
Yeah, people like to say, if you can think it up, you can print it. And basically that's right, because you have unlimited design opportunities, but we need to consider the whole process chain, including post-processing, as it can create a natural barrier, such as how do I get the powder out of the part, etc., something like that. Fabian mentioned that. So it depends on the whole AM process chain to identify the right applications. The total cost of ownership is crucial to consider as well. So for the aerospace industry, typical applications, which we see here very successful, are satellite brackets, combustion chambers, and injector heads, hydraulic components, air ducts. So there are plenty of applications in the aerospace industry, in the satellite industry, and so on and so forth. The tooling industry is of high interest because here it is all about cycle time. And cycle time is related to cooling. If you have a better surface near cooling, your cycle time can be lower. Therefore, tooling inserts, repairs, die casting, and as I said, tool inserts are of high interest and very valuable applications in that industry. In the medical branch, I mentioned one, orthopedics devices like orthoses and prostheses, but of course also implants, hip cups. In the near future, all hip cups will be 3D printed and customized to your personal need. And stands, spinal cages, so the range of applications is wide. And last but not least, the consumer industry. Even jewelry is a nice application. Footwear, sportswear, eyewear, mascara brushes. So there is a wide range, but as I said, remember, you have to start from the problem and work backwards to the solution. Otherwise, you will create a mess.
Fabian, Patrick just told us about a multiplicity of possible applications that we can print in everything from the most mundane consumer goods to, very, very high performance applications, in rocketry, in spacecraft. The natural question any engineering professional would ask about this, are these parts as strong as those manufactured by traditional, say, subtractive techniques?
Yeah, another really good question, Jim. And yes, they are, and they can certainly compete with casting or even forging parts. If you think of it, I mean, Patrick now mentioned many industries, and there's even industries out there that are using additive manufacturing that have just come up in the past or are just starting to enter their foot into the actual manufacturing industry. Think of the space industry that just in the past decade has exploded in North America. Every single rocket engine has 3D printed components out there. Every combustion chamber in the space industry is 3D printed as of today. And if you can print a rocket engine and it can withstand these temperatures, yes, these parts are as strong and even stronger than traditionally manufactured parts. And due to the design opportunities that additive manufacturing offers, can actually accelerate these industries quite significantly. If we think about the EVTOL, the electric vertical takeoff and landing industry, also here electric airplanes that are going to revolutionize the way that we fly. All of these are leveraging additive manufacturing, can only be manufactured and can only be introduced into the market due to additive manufacturing. So yeah, if we look at the metal side of the technology, we can achieve densities of 99.99x% depending on the material, and sometimes more nines than others. And that is because we're fully melting material in the process chamber due to the laser energy input that Patrick described earlier. And yeah, strength is only one material property that needs to be considered. Yeah, heat treatment and post-processing technologies even improve these densities and other material properties even further. And yeah, it is important that you are not comparing apples to apples, right? Additive manufacturing can add tremendous material properties if you're also willing to challenge your current specs. Do you need this high gloss finish that your design currently calls for? Is that just because you've been machining this part for the past 20 years? Do you really need a PA6 in the automotive industry, or can a filled PA11 or other material derivative create an even better part performance? So really challenging the status quo and challenging your original specs, like Patrick mentioned earlier, and designing a part purely for additive manufacturing and therefore for the full benefits of additive manufacturing really opens up a lot of space. And I think one really great example is Siemens. Siemens has been in the additive manufacturing industry, has been a user of additive manufacturing for quite some time. And they've built turbine components where they recently crossed the mark of 1 million operating hours. And if we talk to Siemens, their statement is we have reached a point of no return. We've designed these parts now where they can only be 3D printed. They cannot be manufactured any other way. And yeah, to quote Siemens, if you can build a turbine blade, you can pretty much print anything.
Patrick, Fabian has just told us that we can build strong parts, durable parts. But what level of detail can you achieve with 3D printing?
I hate to say that, but it depends, right? And it depends strongly on the 3D printing technology, on the material chosen, on the component design, and the use case. But in principle, however, let's state some numbers for the powder bed fusion, which I'm very used to. And powder bed fusion, by the way, is one of the more precise technologies, very precise. So what can it be achieved? So we define detail resolution as the achievable minimal wall thickness in Z direction. So for polymer applications, this minimum wall thickness in Z direction is 300 microns. That's a typical grade of detail that you can achieve. And with the new technology, FDR, fine detail resolution, you can even achieve 220 microns in wall thickness in Z direction. On the metal side, we can go below. On the metal side, the minimum wall thickness in Z is 100 microns. In XY, so meaning horizontal built walls, can be even lower. But the typical value to validate the detail and grade is the Z direction wall thickness.
Yeah, and there are certain physical limitations that define these details, as Patrick mentioned. So one is, for example, the powder particle size that is between 20 and 60 microns. And yeah, then we have a laser beam diameter that's around 80 microns. So that's how we typically get to these numbers.
Fabian and Patrick, you've both described very, very fine detail possible with 3D printing. You've also described that parts can be made strong and durable, very versatile. The obvious question that any engineering professional will inevitably come to down this road is, how long does it take to 3D print something? Fabian?
Yeah, good question. And here we need to understand that in 3D printing or additive manufacturing, we typically talk about a build. So we don't talk about a part, we talk about a build, and a build has a certain bounding box. that may be a bounding box of 250 by 250 by 300 millimeters, for example. And this whole build can entail one part, one big piece, or it can contain hundreds, thousands of smaller parts, right? So if we talk about a build, that build can take on the polymer side between a few hours to even over a day. But think about it, you can have a million parts in there, right? Not a million, but you can have thousands of parts in there. So therefore, the print time per part can be in the seconds. On the metal side, also if we look at some larger systems, even here we can start around a few hours of a build, where we could have also a few hundred to even 1,000 parts on there, depending on the size. But also for large thrust chambers that I mentioned earlier, the build time can be over a week, where layer by layer we're building a copper part, for example, that really needs a bit more time to be created.
Fabian and Patrick, you've made a compelling argument for getting into this fascinating technology, and it's so compelling that the logical follow-on question for any attendee would be, how do I get started? Patrick, how would an individual dive into this world and get going with 3D printing?
Actually, I have a recipe for that. In general, most importantly, you have to start early and with a small project and achievable goals. But here's my recipe, my success recipe. So first, look for a problem. I mentioned that earlier. Yes, that sounds crazy, but where is no problem, there is no good solution. So phrase problem statements out of your business. And when I talk about problems, I mean problems like supply chain of components with particularly high delivery times, very complex assembly processes, time-intensive assembly operations, expensive components, just things like that. So phrase some problem statements. Then pick 2 up to 3 of these statements and the root causing application, the root causing component. Then take 3 of your most creative, craziest, and disruptive employees. And now comes the magic. Tell them to design these applications from scratch, focus on component basic function, and design accordingly. Stress your CAD system with the new design. And then take the designs, build them additively, and maybe you use FDM, whatever technology you use. In the early stage, it's not important which technology you use, it is important which design you have chosen. And then learn from the results, make a loop, and succeed. But on top of that, I have to add, it is not about only how to start with designs, it is also about education. We need to get AM in university. We need to get AM competencies and education into any organization. Universities needs to incorporate AM into their engineering, material science, and digital production classes. A recent Deloitte study shows very, very bright and open that nearly 500,000 jobs remain open in manufacturing just in the United States because of lack of competencies. So to support the growth of working professionals in the AM industry, we as EOS even started our own education unit called Additive Minds Academy. So the Additive Minds Academy, therefore, is entering into corporations with universities and institutes in different countries to provide academic programs for students. I just wanted to mention that it starts in school.
And that's a really good point, Patrick. And I think one thing to add to that is that, whatever project you choose, start with an achievable project. Right? Don't reach for the stars, reach for the moon first. And that's already going to be enough, because once you have a first successful project, that will then snowball and you will create so much attention within your organization that, you will then therefore move away from a push into your organization and from a pull out of your organization. And also don't be afraid to get help from external organizations such as our Additive Minds team. We've helped more than hundreds of companies to get into additive manufacturing successfully by, as Patrick mentioned, looking at education and at collaboration and educating your engineers with a joint project. And visit the Academy store and look at our first free e-learning innovation with 3D printing. That's a great way to start. But also, there are some other courses and webinars out there that can really help you to get your feet wet with additive manufacturing. And last but not least, we also have a great podcast called Additive Snack, where we do interview the industry's leaders that give you a bit more tips and tricks and talk about their failures and their successes that they've had over the past decades getting successful in additive manufacturing.
Thanks, Fabian. We've just had a rapid fire introduction to 3D printing. And now you as attendees, you get to access the expertise of Patrick and Fabian yourselves. And you do that by posing questions into the console in front of you on the interface. So go ahead and post questions you may have for Patrick and Fabian in the console, and they will answer them.